quadratic functions and their graphs. We did linear stuff yesterday, so x to the first for the stuff that we were looking at, but today it's going to be about degree 2 polynomials mostly. And we really don't start working with the cubics and stuff until a little bit later. So quadratic functions and their graphs. Come on, there we go. A quadratic function is a polynomial function of degree 2. And we want to know what the name of the figure is when you graph a quadratic. What's it look like, everybody? A parabola. So lines, linear, parabolas, quadratics. And this says we are going to transform the squaring function. So we're going to describe how to transform the graph of f of x equals x squared into the graph of the given function. Now this is important because they're letting us know this is your parent, this is your original. What do you have to do to that to get this graph? That's what we want to do. So g of x equals negative 1/2 x squared plus 3. Think order of operations. We would start here, but there's no transformation taking place here, so there's no h shift, horizontal shift. But we have to tell what these are responsible for. So what's the negative 1/2 responsible for? Vertical compression. Factor 1/2. How about the negative? What's that doing? What's a negative in front? What do?
X-axis.
Reflect over the x-axis. How about the plus 3 in the back? What's it do? Translate up 3. And this said sketch its graph by hand. I guess I'd like to do a little bit better than that because I want to remind you how we go about graphing something like this. And what we do is we consider a part of the parent function for the shape. So when we graph this, we're really going to graph y equals negative 1/2 x squared. And how we typically do that, so we're using more memory than anything else, is by thinking back to graphing even way back in exponential and realizing, hey, these are symmetric. So if I just put like 0, 1, 2, and 3 in here and think about what I would get for x squared, which is the parent function, which is just squaring these, 0, 1, 4, and 9, which usually we kind of memorize even though we don't want to. And then I say, oh, well, all I'd have to do is multiply that by negative 1/2. So this is still going to be 0. This will be negative 1/2. This will be negative 2. And this will be negative 9/2, which is negative 4.5. Bless you. Now this is not going to be my final product, but this is the shape of the graph. So my new parent is at 0, 0, 1, negative 1/2, 2, negative 2, and 9, negative 4.5. Or I'm sorry, 3, negative 4.5. Good grief, I jumped to the 9 piece here. You don't graph the middle ones. And then we can use symmetry to go equal but opposite on the other side. And make this one dashed or dotted. Because that's the shape of the graph. Now, we need to move it. And that's where the h and k comes in. So once we have the a taken care of, we've already taken care of the fact that it was reflecting over the x-axis and that it is compressed by a factor of 1/2. Now it's just counting, because we know we're supposed to move this thing up 3. So we just take some of our nice points and move them up 3. And then again, use that axis of symmetry to go equal but opposite on the other side. There you have it. Like I said, usually it goes faster than that where you're not necessarily having to write down the little table as you go through it, where you're thinking, okay, they always used to come out to 0, 1, 4, 9. If I just multiply that by -1/2, I'll have my new points. But we also graph a lot of things in pre-calculus, so it's possible that you might need to make a table when you go through those. Alrighty, let's look at this one. H of x equals 3, parentheses, x plus 2 squared minus 1. Transformations, what do you start with? You know, if you just listen to me talk and you're like looking at the notes and stuff, you're going to remember about 15% of what goes on in class. But if you actually speak when I ask questions and, you know, just say things, I don't know, maybe you're waiting, maybe you've always had teachers that called on you. You had to wait to be called on. I don't like that. I'd rather everybody just told me what they had. So you remember 85%. If you're participating, if you're talking, you'll remember 85%. So what's the first transformation? To the left. What's the next one? Vertical stretch, factor of 3. Anything else? Translate down 1. So now we know, hey, A is 3 this time. So we could actually kind of just cheat and go back to use this again and say, okay, so my new y's would be these numbers times 3. Well, 0 times 3 is going to give me 0. And 1 times 3 will give me 3. And 2 times 3, I'm sorry, 4 times 3, using this middle column here, would give me 12. And then 9 times 3 would give me 27, which I'm probably not going to graph. But what I'm always doing is using what would normally be those y's and then just changing that according to what our new a value is. So we'd have 0, 0, 1, 3, 2, 12, and that's taken us off the chart already, so we probably just stop with those. Make that one dashed. Nice and skinny and opening up because of that positive 3. Thank you. And we're not done yet. This is what we need to do to it. Where do we move it? A little bit of counting again. And you might want to draw in your new axis of symmetry. I mean, if you're having a hard time figuring out where to go equal but opposite, that never hurts. And there it is. It's actually what we just finished up in chapter 4 of Algebra 2, is getting this out of vertex form, figuring out what are all these transformations, using A to get the shape, and then H and K to move it to its new position, slide it, glide it, translate it. All the things that we've talked about for translations. Now it says, what about A is going to tell us whether or not we have an upward or downward opening parabola? What indicates that? Positive and negative. So if A is positive, it opens upward. If A is negative, it opens downward. That's how we get that, And it's one of those things that before you hand in a quiz or a test, you go back and, hey, does this stuff open the way that I know it's supposed to open? Are all the transformations that I saw numerically happening in this picture? Was supposed to get wider by the compression, then it should be wider. For a parabola, the line of symmetry is its axis of symmetry. Line of symmetry is the axis.
Go to under the scroll, yeah. Yeah.
Oh, and this one?
Yeah.
Rats. it's not gonna let me. There it goes. Okay. Slide that up there. It's supposed to be. Slide that up there. Thank you. Axis of symmetry. What's the equation always going to be? X equals H. X equals H. Now, where the heck is the H coming from? Well, from this. That's the vertex form that we have for the axis of symmetry. Now, if it's in vertex form, then it's really easy to find. But sometimes we have to do a little work when it's in standard form. And standard form is that ax squared plus bx plus c. And that's going to be negative b over 2a when it's in standard form. That's how we'll get that axis of symmetry. So, little formula there. But you know what? We're going to be doing completing the square anyway because we really want this vertex form. It's super easy to find what you need for vertex form. And we can make all of our standard form equations look like y equals a times x minus h squared plus k. Put them in that form, and then we'll have what we need. So the parabola, the line of symmetry is also its axis of symmetry. Axis for short. Books will use those words interchangeably. Line of symmetry, axis of symmetry, it's the same thing. It's where you fold it over and you get the same thing on both sides. So what is the special name for the point on a parabola that intersects its axis? What is the vertex? So that axis of symmetry is always cutting right through that vertex, and that's why it's x equals h, because our vertex is hk. And right here we can see, we've got our Cartesian coordinate plane with one of these that opens up because A is positive, and then we have one where A is opening down. And the axis of symmetry for both of these would be the line x equals 0, because we're karate chopping the x-axis when we draw this. And so it gets its name from that action, x equals 0. So no shocker there. But if we do have an h that shifts it, well, then the axis of symmetry is going to move according to that, so it will be x equals h. And away we go. Expanding f of x equals a times x minus h squared plus k. What do they mean by expanding? Writing it out in standard form. There's a problem with this that makes it take a little while, and that is we cannot distribute those two. We've been talking about this. You can't distribute that power of 2. You have to literally write out a times parentheses x minus h parentheses x minus h plus k, and then doing all the math. So that gets us our standard form of a quadratic. Ax squared plus bx plus c, where the powers of x are arranged in descending order. Remember, that's standard form. We can obtain formulas for h and k. We're not going to use this. I mean, we just aren't. The book uses this, so I want to make sure that you understand how to do this. But the algebra behind completing the square is what you need when you get to calculus. It's not that you complete the square every day in calculus, but it's the difficulty level of the algebra that you need. So if we have f of x equals a times the quantity x minus h squared plus k, we would have to do this obnoxious bit of math to get this to work. So the first thing we would do is we do the FOIL and get x squared minus 2xh plus h squared when we simplify that monster. And then we'd say, hey, I have to distribute the a through that. Won't that be fun? Ax squared minus 2ahx plus ah squared plus k. Oh, doesn't that look nice? So we'll break that down and we say, here's what we know. The first term is the squared term, so we need the x squared piece. Oh, good news, that's just ax squared. That's not a big deal. But anything with the x is going to be my middle term, and that's going to be minus 2ah. And we factor that back out. So you distribute the a, and then you factor that back out, so the x is by itself. That leaves this mess right back here for k. Because we treat it like ax squared plus bx plus c. So here's what they're trying to tell us. If we have all of this in vertex form, we could figure out what it is in standard form if we want to memorize formulas. B comes from -2 times A times H. And C comes from AH squared plus K. I don't memorize formulas. You know, I just don't. I've done math my whole life, and I'm not a memorizer. I'm just not. What I want is the math that leads me to what I need to do, and I want it to make logical sense. So the book has this in here. Fabulous. Great for them. But 6 months from now, you won't remember that formula. What you will remember is how to complete the square. And that's the reason that we divert from the book at this point and do completing the square. So this says, let's just say we had to figure out what H was, and we had to do it with these obnoxious formulas. Well, we'd have to divide by -2 and A. And we should recognize that as the shortcut when you have it in standard form to find your axis of symmetry, which is also your x coordinate for your vertex. And then if we solve this little monster for k, we get c minus AH squared equals k, which again, I find is a totally useless formula because completing the square will take care of all of that. It'll be more logical. But you just need to know that that's out there. And if you're a formula memorizer, hey, then I guess you can have a little fun with these. But we want a logical process to find this. So this leads us to the fact that any parabola can be written in vertex form. And we're going to make it happen. We're going to do that. So any quadratic function ax squared plus bx plus c, which is in standard form, can be rewritten in vertex form by the process of completing the square. The graph of f is a parabola with a vertex of hk, axis of symmetry x equals h, where you can use these formulas if necessary to figure out what h and k are. But for us, it's not going to be necessary. A is going to open upwards, A is greater than 0, then it's going to open upwards, and if A is less than 0, then it's going to open downward, which we already knew and we already answered questions about. So, something else that is connected to this, the quadratic formula. You remember it? How many of you learned it as a song? Okay, we had some teachers that don't sing it. So, it's to the tune of Pop Goes the Weasel. X equals -b plus or minus the square root of b squared minus 4ac up over 2a. Worthless. That's what I call it. We have no idea whether or not we're getting the right answer. We have no idea whether or not if we put that in, things are going the right way. Now, this is a backup plan. The quadratic formula is always a backup plan. If you don't know how to complete the square, then yeah, you better use the quadratic formula. But you have calculators that will already find the zeros for you if you're taking the MCAs or the ACTs, and you don't have to memorize that formula to make that happen. So we're going to learn about completing the square because we do know what it does. Do you remember what it does? What are you getting when you do the quadratic formula? The x-intercepts, the zeros, the solutions of the graph. So the quadratic formula is a backup plan. That's what it is. It's a backup plan. If you've forgotten how to complete the square, if you've forgotten how to factor, if you've forgotten everything about how to solve a quadratic, then you could use the quadratic formula. So, what do we want to do? Well, we want to transform these and we want to learn how to do it by completing the square in multiple pieces so that we're able to manipulate things with algebra as difficult as the things you'll need to do when you get to calculus. So, use the vertex form of a quadratic function to find the vertex and axis of the graph of this. Rewrite the equation in vertex form. So the first thing we're going to do is we're going to make this a y, and we're going to put this in standard form. So we take a look at it, and we realize, well, that is not in vertex form. And if I'm going to complete the square, I know for certain that that 5 in the back is not going to help. So I'm going to go ahead and move the 5 over right away. All right, so now we get to the heart of this, the meat of completing the square, which is, this has to be a 1. You cannot use completing the square unless the number in front of the square term is a 1. So we're going to go ahead and divide both sides by -3. So that we have this in a place where we can complete the square. Now I know the left side is making some people nervous. Don't worry about it. We're just moving things out of the way. We're going to move them back when we're done. It's just keeping stuff out of the way that we don't need right now. So now what I need to do is figure out the number that will complete the square over there. You remember the little formula? Yeah, most people that one will come back to. B over 2 squared. So ax squared plus bx plus c. So here's our b. And we realize that's going to be -1 squared, which is just going to be 1. But here's the thing we have to remember. This is still algebra. Whatever we do to one side, we have to do to the other. Like I said, now people are getting a little worried about that left side. Well, all we're going to do is give it a common denominator so we can put that stuff together over there. And we look at this and we say, okay, well, the common denominator here would be -3. So I'm going to have y plus 5 over -3 plus -3 over -3. And I'll just leave my right side alone for a second. And now that there's a common denominator, we can go ahead and do the addition across the top here. So y plus 5 plus a -3 will really be y plus 2 over -3. And now I'm going to put in the whole reason that we use this method. We made that a perfect square trinomial. We did that by adding that 1. So now we have to figure out that, well, it was an x that we squared to get this, and it was a -1 that we squared to get a middle term of -2, and to get a +1 in the back. Now that, hopefully you're looking at it and going, yes, now it's starting to look like vertex form. That's what I have to have in order for this to look like vertex form. Now all I need to do is move the other stuff back over, because that's all we have to do. To undo division, you multiply. So we're going to multiply both sides by -3. And at this point, usually somebody says, should we distribute that -3? What do you think? Should we? No, we want a x minus h squared plus k. And we're super close, because all we have to do now is move this 2 over. It looks like so. I don't want to scroll up since I'm recording, it takes so long. So the question was, use the vertex form to find the vertex on the axis of the graph, and then rewrite it in vertex form. Oh, we have it in vertex form, there it is. So our job is simply to tell them what the vertex is and what the axis of symmetry is. So what's our vertex? 1, -2, it's right here, HK. Axis of symmetry. Remember, right chops the x-axis, x equals what? 1. Yeah, there's our x right there. Cool. So we're going to complete the square, then we can find the vertex and the axis of symmetry very easily. Now, if you wanted to double check that with the formulas they have, we're totally all right with that. But one of the things that Mrs. LaRue has said continually over the last few years is you guys have to be really, really good at algebra. You have to be really, really good at manipulating, at moving things, and that hadn't happened in prior years. But I'll tell you what, she's done nothing but brag about the fact that the students are doing really well this year with their algebra. So that's what completing the square is going to do for us. All right, why is it bringing me back to that? That was not it. Here's example 6. There's example 6. To describe. That just must have gotten saved with all of the stuff on top of it last year, huh? Oh, let me get that stuff off. Come on, here. Oh, I knew at some point it was going to give me a lot of trouble because of all the recording on it. But where did it go? And it totally scrapped that page just now. So, give me a second. Where did it put it? Already did that. Already did that. And example 6 has disappeared from the planet. So let's try it again. There it is. Oh, be nice, smartboard. There we go. All right, let's use complete in the square to describe this graph. 3x squared plus 12x plus 11. But this time I'm going to let you guys talk me through it. What do you want to do first? What's next?
Divide that.
What's next? B over 2 squared. Tell me what you get. Plus 4. 4 divided by 2 is 2, and when we square it, we get plus 4. All right, so what should we do next? Okay. Everybody see what Emmy just did there? She said, hey, if we need this in thirds, it's 4 over 1 right now. So that's going to have to be 12 over 3 to make that into 4. What's next? And don't tell me, do the thing with the thing. Give me the names for this. Factor. How? This is called a perfect square trinomial. What is this going to be called? A binomial squared. What binomial? X plus 2. Now what do we do?
Do the thing.
Yeah, the thing with the thing. Multiply by 3. And that wasn't so tough, right? Not awful. Okay, so what they want us to do with this? This said, use the completing the square to describe the graph and put your answers graphically. Well, that would mean they want to know where's the vertex, all that good stuff. So where is our vertex? -2, -1. Axis of symmetry is, of course, at x equals -2. Is this going to open up or down? Opens up. And just for good measure, is it going to be skinnier or fatter? Skinnier, yeah, we're doing the 3. And we could certainly, throw it in the graphing calculator to get exactly what it's supposed to look like. But here's the key. If we were to graph this, we would want to make sure that our vertex is at -2, -1. We would start with that y equals 3x squared as our parent function, and then we'd just move it. That's all we would do. We would move it. And would end up with this. So what we see with the graphing calculator needs to match our math so that we know exactly what we have going on. Alrighty. Write an equation for the parabola shown using the fact that one of the given points is the vertex. Like that's some big hint or something. We can see that's the vertex. Huh. To write one, we need h and k. Cool. I also need a. I don't have a. How can we find it? Yeah, use the other point. What is the other point going to go into our formula for? X and Y, yeah. Remember, that's what the X and Y stand for, any point. So we put in what we know, and then we'll just solve for A. So 5 equals A, 1 minus a -1 plus a -3. I'm just going to make that a -3 right away. I probably would have normally made that 1 minus a -1 plus right away too. I want everybody to see the steps. So we're just putting in h and k and x and y, and we're going to do some math. We'll see what we get. Well, 1 minus the -1 is 2, and 2 squared is 4. So 5 equals 4a minus 3. We'd add 3 to both sides. We would divide by 4. And now we can write it. We have a, we have h, and we have k. So y equals 2 times x plus 1 squared minus 3. And we got it. It's not a big deal. Did that now? 2. Yeah. So characterizing the nature of a quadratic function. What on earth are they talking about? We could see these in a lot of different forms. In the verbal, they're going to talk about how we have a polynomial of degree 2, or we're going to figure out that we need a polynomial of degree 2 to represent whatever it is that we have for our word problem. Algebraic, we've got our standard form or our vertex form. Vertex form is often more helpful because maximizing or minimizing takes place at the vertex. So we really like that one. That's the reason we do the completing the square. Graphical method, parabola. Vertex at hk, axis of symmetry, x equals h. We know when it opens up, a is greater than 0, opens down when a is less than 0. And if it's in standard form, you can always get 0c as an easy point, because if you put 0 in for the other two x's, they'll drop out. And then your x-intercepts fall back. You could always use the quadratic formula to get those. We would try everything else first, I'll tell you that much. We would try absolutely everything else first. Including all the factoring that everybody has ever learned, and the graphing calculator, and then we'd say, okay, let me put this in the quadratic formula. And like I said, really one of the few reasons that we teach the quadratic formula is because if you've forgotten everything else, people usually remember the little song. It's a fallback. So today, we were talking about our quadratics, trying to meet one of our many objectives for this section that we see up there. And it's using quadratic functions. We're not applying them yet. We're going to do word problems on Tuesday. You guys are off. So 4, 3, 2, 1, 0 me on how you feel about parabolas, quadratic stuff that we've been doing. Okay, looking like pretty good numbers. A lot of people that don't want to teach it to somebody else but feel like they know what they're doing. So that is good. And my smart board will be happy that we are done. Because it did not like